all the vapor covered with this surface, it doesn't really matter how this surface looks like. So because when all the vapors cover this surface, there will be a surface, vapor, and liquid. And this vapor will function like a barrier. So no matter how good your surface is, it still has to go through this vapor. So the film bonding doesn't really show very much difference. So you can see these three curves overlap with each other. The blue line is this one is the normal surface grounded. Green one is the PO15, and the red one is PO45. But you will see here will be the interesting part. The PO45, they have a very high very high electrolytic point temperature. Here is the wall superheat. Actually, the wall superheat is around 80 Kelvin, which indicates 155 Kelvin, which is very close to the pure aluminum experiment. So that's also a sign says my experiment is correct, because I can repeat this one with although with different surface, with the same structure, with the different surface, we still able to get something similar. And when you look at it here, you will see PO15 and PO30 is very, very similar.
Thank you.
It didn't show much difference. But when you look at the critical heat flux, the highest value you can see here is more than 90,000. But here is around 60 and 30, so that's still three times increasement. And also when you look at this time and temperature curve, you'll find three curve will be very interesting difference. You can see here, the curve has a very strong transition point, which is here, and that is the electrolytic point, and the slightly smoother nucleation bonding here region is going down smoothly, so which indicates we don't have a huge critical heat flux. But when you look at this red curve, you will see it's almost vertical. The more step you have, the deeper you have, usually means the higher critical heat flux you're gonna have, because you have a temperature decrease with a very limited time. But when you can see here, it's kind of in the middle, and also we still can see two steps here. This one and this one, and which shows here the turning point is smooth. You can see a round corner. It's not a very sharp corner. It's a round corner. The rounder you have, that means you got two different stages, which is very similar to what we done years ago on the pure aluminum surface. And here, this one is a very interesting one, and this one is very hard to explain to you. So please be patient. It's a lot of things inside in this figure. So for this one everybody have seen that one already. That's the horizontal with the temperature, superheat, and the vertical is the critical heat flux. I just zoom in this small area, which is the transition bonding and the nucleation bonding. And here, this curve shows the up and the lower limit of the active bubbles. Because a bubble has this upper and lower limit. If it's smaller than a limit, it won't survive. But if it's bigger than their limit, they will touch the cold fluids. When they touch the cold fluids, they also collapse. So you have an area which the bottle can survive. Okay, here we calculate with the theoretical model, and they give me the area. How big is the range going to be? So the red line here still refers to PO45. Green line here PO15, and the blue line here is normal surface. Then I will. Is it a question, Dawson?
I got lost.
Okay.
So the blue line doesn't have a sharp jump anywhere between for superheating between 0 and about 50K. Is that right? It's just
yes, because when they reach about 48K, they change it to the film bonding. If it's in the film bonding, there's no coverage, there's no bubbles.
So this vertical line down the middle is the onset of film bonding.
This vertical line?
Yeah.
That's the end of transition bonding.
And it's also the onset of
film board.
Yeah, the start of the outside, start of a film.
If you move to this direction.
Yeah, move to right hand side, there will be a film board totally.
Okay. Got it.
And there's no bubbles at all. So there's no use for us to talk about the bubble size.
Okay. Got it.
Okay.
Got it. Thank
Good.
you. Yeah.
And then the third one is when you have okay, here we provide you with the upper and lower limit of the bubble size, right? And then we have the distribution of pore sizes on the surface. And then we correlate these two together. Let's ask a question. How much percentage of the pore on the nanopore sizes is turned into activate? Which means how many nanopores actually functions? Because they give you upper and lower limit. And then I want to know how many things in between. But we have the distribution already, and they give you upper limit. Okay, then we do the very easy integral, and we try to find the percentage. When we have the percentage, and also we have the number density. When we have these two together, they will told us the number is how many pores is functions. When we have how many pores is functions, actually, according to Dr. Chen's previous students' molecular dynamic simulation, they told me the pore size is not all the area is functions. It's only the contact line, which is solid, liquid, vapor contact line. That is the area which heat comes into the bubble. And then we time this one with and the contact line area. It's a circle. So when we time them together, they will give me one number, which is how long is the total contact length of one surface, which turns into function of the bubble generation. And then this is shown in figure 3. So we can see here the red line. Red line is the PO45. They say all of the bubbles into it. All of the bubble functions. All of the functions. But this green line is only about 60% of functions. So that means if we assume the heat transfer from this contact line will be the same. If we assume that will be the same, which means we have more area which heat can go into the bubble. So naturally, we will have a higher heat transfer. If we have a heat transfer, we will see a higher critical heat flux and a more steeper nucleus boiling curve. So this is what we see here. Does everybody catch this logic? Okay. It's kind of hard to follow because it's a lot of things involved together. And the purpose one is the quenching, and this one is the heating. Still the same logic, and still a very similar result, which is this PO45 they pump to the maximum at the really beginning. So that means just give him a very little heat, it all turns to the bubbles. They give me huge heat flux. That's what we want. Okay, this one I didn't want to show anything else. I didn't want to show the repeatability and stability. I have called in the very beginning of a literature review. We have seen somebody using a similar structure and use water. The effect is declining. But when we use the liquid nitrogen, it's pretty much constant. So there can be two different reasons. The first one is when you have water, although you still have the same superheat, like around 80 Kelvin, but the saturation temperature for the water is way higher than liquid nitrogen. It's like a liquid nitrogen is 77.35 Kelvin for the saturation in the atmosphere, but for water, it's 373. So a large temperature increasement. And when you have a large temperature, there's more heat, so it will probably increase the possibility to destroy the surface. That literature didn't really give me the SEM after the experiment, but my SEM picture is all taken after the experiment. So the SEM I took is showing you that the structure maintains. The structure is still there, and it's still working perfectly. And also another reason is in the water, the probably got oxygen and other gas dissolve it. When you have heat coming into it in a very local area, maybe there's some chemical reactions. But that paper doesn't really give any answer or any suggestion to that. I'm not quite sure. For liquid nitrogen, which low temperature and also almost no, it should be no chemical reactions. So this will maintain the same.
Is your nitrogen pure? No dissolved oxygen?
In the liquid nitrogen,
Yeah.
I will say yes, because I what I do is I clean my dewar for 5 times before the experiment. So I clean it first, in case there's something dissolved. And the second part is the molecule simulations. This one is also interesting. There's three questions I want to answer. First one is I want to see how the bubbles spread on the surface. Very interesting and very easy things. I don't even know how droplets spread on the surface. So what's for? Yeah, but there's something behind it. And also I want to use the Lennard-Jones potential instead of very complex so-called quick potentials. I want to reduce it and also get something similar result. And the third one is I want to see if with different surface energies, how the content is going to look like. And also if there's any theoretical or semi-theoretical solutions which I can use to predict. Okay, here is the droplets. Here, let's look at the figure here. This is droplets. The green one is hydrogen, red one is oxygen, and the blue one here is the base surface, that is aluminum. And it was aligned and was put into the right position before the experiment, before the simulation. And this is a mixing law. This is a very widely used mixing law here. And there's 2 parts in my potentials. One part is Lennard-Jones, like here, so-called 12-6 rules. Another one